Hello and welcome to another video. And today we have a Prime B450M-K on our bench. This is a DDR4 board, AM4. And already I can see that the PCIe latch is missing. Just again on an ASUS board that the PCIe latch is missing. And we also don't have a battery in here. And yeah, so we will have to repair this battery latch as well. This board came for me for starting up but not booting, so there's there's a reaction to the power button, but the board doesn't go any further. And yeah, I would say let's build this board up together. We will be putting this into here, the 2200G. This is an APU, so we have a video output here, so we don't need a graphics card and can exclude all of those possibilities. Also, one stick of DDR4. This is just a random 4 gig stick that I always use. Then we're also going to be using the DDR postcard that I have for the DDR standard right here for postcodes. On ASUS, there's a COM debug port right in the bottom right here where you can plug this board in with the TPM header first. And looking at the orientation, that pin 1 matches the pin 1 on the board. If there's anything going to be on there, I will be showing you that as well. And yeah, next up, let's connect the power supply. So we got our Pico adapter connected right here. We have everything built up. Let's open up our power supply and connect it. And we have passive power consumption, 133 milliamps at 13 volts. Don't mind the 13 volts. This adapter can handle the 13 volts just fine and convert it to the 12 that we need. And we can see the 5 volt VSB standby lights. Oh, this might be 3 VSB standby lights. Let's get a power button in the speaker. So speaker down here. And also a power button down right here. And let's see at the power consumption right there and see how this board behaves, and also at the DDR tester. So we have 973 milliamps right now. So almost an amp, but we have static, so there's nothing moving here and nothing moving on that tester. And the current is very static that we have. So nothing changing. The CPU is not getting hot at all. Let's clear the CMOS. It probably is cleared because the battery wasn't in there. But let's see. Does it react to the power button when turning off? It seems to be it does not want to turn off that one. Okay, we're just going to cut its power. And I will show you the way to clear CMOS the actual way, because I was fooled for a long time how to actually clear it. Let me show you on the microscope. What you want to find is this clear RTC section where you have two pins next to each other, and this is the actual way to clear a CMOS. So you want to be bridging those two contacts, because I thought before that connecting the battery power, the battery supplies, so the positive and negative of the CMOS battery actually resets it every time. But I found out that especially on newer boards, that doesn't happen like that. So you will have to find these, or maybe a button sometimes that you can short, and that will actually reset the BIOS. And I also want to show you this port right here, because this is the COM debug, as you can see right there. ASUS uses these for debugging, and we're going to be using that with our PCI adapter, and we're going to be using this TPM header. This has a number 1 marked here for that pin, and the marked pin on the board is the one that has these this white square here. So this here is pin 1, and we want those to line up for using the postcard. So we've now reset the BIOS. So let's apply a voltage to it again. And let's press the power button again. And we still have 950 milliamps. So basically the same, no change at all. The tester and that tester not saying anything, CPU not getting warm. And if you've seen my last videos, you probably noticed that this power supply is new, that this wasn't here before. And what I'm actually using is something very interesting, which is this little thing right here that you can see. This is from FIA, I think they're called, which is this little neat box right here. I am very proud to announce that they have sponsored our channel with tools, and they've reached out if I was interested in any. And I saw this portable CNC DC power supply. And the interesting thing is, this isn't the actual power supply that you would expect it to be. This is a DC to DC converter. This is not a AC to DC power supply. This thing regulates voltage for you and regulates amperage also. The really interesting thing for this is, this has a flip up screen. So really good viewing angles, as you can see. This is probably an OLED. Don't quote me on that, but the viewer angles are really good. You have input outputs at the front that you can turn off and on, and that have visual indication, as you can see. On, off, on, off, with this button right here, which is really cool that you can turn the input out on and off, as you can see by the amperage also. And which is really interesting also, this has various inputs. So this is micro USB. This is for connecting up to the PC. As you can see, this is for this software that's currently not connected, for being able to show you. And then what I also have is a switch from going between DC and PD. Let me change the focus. So as you can see right now, this switch says PD or DC. So you have multiple ways of inputting power here. You have power delivery, the power delivery standard that you have on many plugs for like phones and different stuff. So you can power this via USB-C, and it will be using the standard of that. And you can power it by a DC power jack from 5 to 32 volts. And I'm doing that with this adapter right here. But I've found multiple interesting ways to power this thing via power delivery, which is really cool, which I want to show you right now how I did that. And then I will show you also some options that this thing has here, and we will be looking at that via the PC, because this has full software support with the computer. So first, let me show you one really cool way of using the power PD here. So this is a power bank that I use a lot, a really big power bank to be fair, and this supports also 12 volts via USB. And if we connect that and turn on the power bank, you can actually see that this thing is being powered via the power bank. And also you can see the input, 12 volts. Oh, well, you can't really see. But what I can tell you is that this can power our main board. We turn it on, and you can see that the output is on by these lights, and that the board is actually on. And again, we can turn this on. This won't update right now because I don't have it connected, but you can see it right here. It's drawing 1 amp. It's drawing a little bit more because the voltage is lower than before, but we have the same thing. The board is still stuck, but we're currently running all of this. We're testing it off of a power bank, which is pretty cool. Like, we're using the 12 volts coming out of this power bank into this DC to DC converter board. Then it's going into a Pico adapter, which converts 12 volts to the PCIe standard. And with this, we have a fully portable setup to diagnose mainboard, which is really cool that this is actually possible. And yeah, you can basically plug any phone charger into there that supports actual power delivery. You do need to be careful of the amperage limits that you have for power delivery, because this can only supply as much as your power source can supply. But yeah, USB-C, I don't have an actual good power delivery system. So what I'm using always is just my DC power, lap bench power supply to supply DC to this barrel jack right here at the end. And yeah, I want to show you the software right now. So I'm going to be taking this off again and bringing back my power bank, and we will going to be having a look at the software that this thing ships with, which is just great, really cool. Let me show you that. So now you can see the actual power supply software, which is really interesting. This thing, as soon as you connect it, and now it's connected. As you can see, we had to use COM port 3, and this is the DPS 150, which is the name of the device. And it is currently connected, and it is key locked, which is very interesting. So you can't do anything on the power supply itself. It's now completely controlled via software. And the very interesting thing is you have voltage settings, which currently is 13 volts. The upper limit is 20 volts of this, and you have a current limit of 5.1, which is the only thing that is kind of bad for me, because as you may know from previous videos, stress testing boards sometimes gets up to a limit of 10 amps. I've not really had it that it exceeded 10 amps, but it is only for running condition that it ever will go over 5 amps. So these 5 amps will be more than enough for starting up, getting into BIOS, which is the most important thing for us right here, that we want for diagnosing a board. We want accurate current measuring, and that we will get this with this. I would have, if I could have wished, I wished for at least 10 amps here, but we will be just fine with 5 amps. As soon as I will be stress testing the board, I won't be connecting it to the power supply then anymore. You can actually control the brightness also. This is what you see. This is the output voltage and the output amperage. If I open this up, it is still connected to the board, and we have the passive power consumption at the actual voltage output. And you can see also a graph right here that is actually running all the time also. There are more measurements like output capacity, output energy. If you're charging lithium ion cells or similar things, you can actually see how much you put out. Express data, I don't even know what this is. I think these are presets that you have right here, where you can program voltages and amperage limits here. And that is also a big thing. This has an amperage limit. If you've seen my last video where the VRM blew up, this would have been great to have. And now I will have that. And yeah, this thing is pretty insane, because not only have you this page, but there's an advanced page where you can actually program cycles, start number, stop number, and you can really program this thing and data log it also. As you can see, you can start it and then data log all of what you're putting in. So this is really scientific, this thing. This goes way beyond the scope of what we actually need to fix ATX motherboards. But it's really cool to see that it can do all of these things, like output current, voltage start value, voltage step value. Like, imagine what you could all monitor with this thing and analyze. Like, yeah, going in different steps with different voltage settings, seeing how circuits react this thing is insane, and I really love it, because I was struggling before with showing you the amperage that I was taking. I got a lot of questions before. I was using a inline amp meter to show you that, but now I got an actual digital output that I can just input into my OBS and show you that, which is way more consistent and way easier readable. I can't imagine how difficult it was before, when it's only on a phone, for example, to read the output that I had before, and now it's gotten really easy. So let's go back to the overview. So this was the first thing that they supplied, and they also supplied something very similar, which is different from what we need. This is a USB tester, the FNB58 from them, and this thing supports so many standards. This thing supports all of the quick charge standards, and can analyze the power input that you have from it. So let me just give you a quick rundown of this, because I'm not a laptop repair guy. If you would be repairing laptops, this would be even more insane to use. But for me, I will be using this to test the USB-C on some boards, because the USB-C often fails on boards. And let me just show you briefly how this works, because this is not my cup of tea, but still is an insane tool. So it has various inputs, as you can see. It uses either Type-C or micro USB, and you have one output, which is Type-C, and you connect it either via that or that to your PC to also have data logging and a software. Yet again, oh no, you use this, and these could be also monitored. And you use this for connecting to PC, and there's a full interface with a scroll wheel for right and left, a back button, and also a OK button if you press this wheel in. So let me show you if we connect this up. So right now you can see the 5 volts. This is 4.9. It's kind of hard to see the 4 right there because of my overhead lighting. And you can see amperage limits and voltage. And this has also this for the voltage. And it has also this, which is way easier to see, the amperage and the voltage. There's nothing connected to the output, and it also flips with the direction, which is very cool. And my power bank turned off. Let me turn it on again. It boots quite quickly. You have these different windows, and let me connect up something to the charging so you can see this thing in action. So right now you can see, and I will be plugging my phone in, and now we are quick charging. Oh, this shouldn't be quick charge. The power bank shows quick charge, but this isn't quick charge yet. You can see 4.8 volts at 0.45 amps for almost 5 volts. Now it went up to 0.8. Let's see. I'm using a output that isn't supporting quick charge. Let me get a USB-C cable to properly show this. So now we are connected via USB-C. You can see the 5 volts with 0.4 amps. And it's trying to negotiate, but I have a OnePlus 7, which has a weird standard of quick charging. And I don't know if it can supply that. But what we can do is, if we go into the fast charging, there's actually a detection mode for all of these standards here. So you can see right now what this supports. PD, Apple, BC12, Samsung AFPC. Like, if you know this probably tells you something, but this can analyze what kind of protocols are supported and which are not, which is really, really cool. Like, I don't have a clue about this, but yeah, it works pretty neatly. Oh, I got back into that. Let's see. Let's run it through once more. And this has more things like PD trigger, MIPD trigger. Like, I don't even know what all of these things are. Like, I'm sadly really not into that much. If you were probably into laptops or phone repair or tablet repair, you would probably know this better. And there's also statistics, settings, toolbox. Don't even know what this all does. Cable resistance detection, PD listener. Oh, a PD converter, USB-C, E-marker. Like, this thing has so many functions, and I will be definitely using this in the future and be getting adjusted to it. But this screen also on this is very cool. And again, it does data logging. So you can be doing output to your PC and with data logging included, which is just so cool that I've made software for their things, which is one of the most important things for me. So yeah, I was able to briefly show you both of these things, and just thank you very much, Fnizi, for the support and with sending both of these over. And yeah, I got to mention, they didn't say anything of the talking points that I have. They completely let me say and do whatever I want with these things. Like, there was no obligation to do anything with them. They just wanted to send them out to me, and that I could do with them whatever I wanted. There's only a single thing that I would say annoys me about this thing, about this one, which is that the barrel jack at the back is not the standard barrel jack that you have on basically every other thing, but I had an adapter laying around and I was able to connect it with that. So yeah, not a big thing, but still. I'm really happy for that, and it will enhance our videos greatly in the future with having this right there for the output current. So really happy. Let's go on with this repair. So regarding this repair, there's actually, we could now go into like measuring the voltages all on the board, seeing what we have, what we don't have. But I was actually provided a very interesting image of the seller of this board that I want to show you right now. So what you can see right here is the image that I was provided. And you can see this is the SIO right here. And this was the included picture with it. There's a knocked off component close to the SIO, probably a resistor. And as you can see, there's a lot of flux on here also, which means someone has tried to fix this before. And they actually were able to find that, which is really good. Like, they actually found the problem. So I bought this board basically knowing what will be wrong with it, pretty surely that this is the reason why our board isn't starting up. Let's have a look at the board view and see what this missing component here is. So now in our board view, we go close to the SIO and we have these two resistors. This right here is a 4.9K ohm resistor for 12 volts. That is 12 volts coming in. And this is our missing component, the top one, which is also a 4.9K ohm resistor, 4.99K, basically 5K. But the important thing is this is a 1% resistor, as you can see right there, because as far as I know, this is used for monitoring 12 volts with the SIO, and this is a shunt, basically. So the value of this is very important. So I will be needing to find a 4.99K ohm resistor on a donor board that I have. And now we are on the board view of a donor board that I have. And in the VRM area, right here at the top, you have R72, which is a 4.99K ohm resistor with 1%. Exactly what we need. So I have board views and schematics for my donor boards, so I can easily search in them. I will show you how I always do that. So this is the schematic of one of my donor boards, an MS7B47, which is Z370, I believe. Yeah, Z370, an MSI board. And what I always do is I just search for my component. As you can see in the top right, there's my search bar. So what I do is 4.99, which is what we need. And I have, let me see. And we currently have 8 results. So I go into them, and then we can see that there's actually a match. As you can see, we have 8 matches and we have 4.9K ohm resistors. This is always what I do. And then you can see R92, and I just search for R92 and R72 and so on. I just searched that in the schematic and was easily able to find these. So this is the way I always search for components on donor boards. So right now we need the resistor. And it is from this donor board that I have right here, which has a burned area around the PCH right here completely. And we will be going under the microscope, as you can see, completely burnt. And we will be taking the shunt resistor from top there. So I will be quickly desoldering that, and then we will be putting it on our board. So this is now our area where there has been work done, and also where our component is knocked off. As you can see by the flux, someone has really tried to fix this board. And by the soldering pieces right here, this resistor has been chipped. Oh, you can see this resistor right here has been chipped. Then you can see this is kind of burnt. There's a little bit of chip here. Let's see, is there anything else around the SIO? This resistor looks like it has gotten something. Yeah. The rest looks fine, just like the SIO itself. Scratches definitely. And yeah. So this is our area where we will be needing to put our resistor. And I've already desoldered the resistor. So there's our resistor right now in place. And what I always do to be able to properly fix the resistor in place is I just tack on one side. So we take our soldering iron and we just want one of the contacts to be connected already. And this is very important. If we use hot air now, the resistor won't fly away. And we will be taking some flux onto here so that it will flow properly, and the solder will also be nice and puffy and shiny. And now we will be taking our hot air. And now we want to heat up the area. The solder is melting pretty quickly, as you can see. And now it's already connected. As you can see, by touching it and by moving it, it pulls back to its original position, which means it's properly soldered in. And this happens because this is leaded solder, which has a very low melting point, and also there's a good amount of flux, putting good heat into there. And I will be cleaning this area up now. Let's use our handy little alcohol bottle that I always use with some cotton buds. And we will be cleaning this area up, getting rid of all of the flux. So now our area is cleaned up. We have got our resistor soldered in. And let's now see if that actually fixed our problem or not. So let's see now. We will be turning on our power supply. As you can see, we have 133 milliamps. And yeah, let's see how this board will react. Let's watch the amps closely and also the testers that we have on here. Pressing the power button. We got higher power consumption. We have 1.4 amps. Is the CPU getting hot? The CPU is not getting hot, and I'm not getting anything on my testers. Oh, the CPU is getting warm. Okay, so the CPU is getting warm, so there is something happening here. But with that static amount of current consumption, I wouldn't expect this board to be turning on right now. So the current consumption just jumped a little bit because of the fan that I've connected. But I don't think that we have any boot. Let me see. Let me put in a USB keyboard for indication. But yeah, still nothing. So still, the board still isn't working. But CPU is a little bit warm. So very interesting. So what I would be guessing is that there's more physical damage around this board. So let me have a look closer at especially the SIO area and measure some of those components and see if they are still intact. And would you look at this? There's no repair without this happening. Someone has tried to flash the BIOS on here. The soldering looks okay, to be honest. Like, even the connector is still intact. I will have to see if any of these components, like the middle one on the top and the bottom one, is missing or is supposed to be missing. But yeah, there's definitely been soldering in this area. We'll have to check for all of the components that are supposed to be here. And I think that we will have a dead BIOS on here, like something that isn't right. So what I will be doing actually, I will be going over the soldering just to be sure here. And I will be using this pin header right here to flash the BIOS, because this pin header is directly connected to the BIOS chip. And you can connect your adapter to here, which I will be doing, in order to connect to the chip and then just program it in circuit. Hopefully it works, because my program has a current limiting. But yeah, let's see if that is possible to do. So we'll look at the board view again, and we go to our BIOS chip, which is here. Oh, it's flipped. It's a little bit different on this board view, actually. Interesting, because we have it, I think, the other way around. Yeah, we have it the other way around, but it shouldn't really matter. But what does matter, we don't see the passive components actually that are supposed to be sorted in here. Okay. But the chip is, I think, a similar one, 1.8 volts, which is important, and 256. So this is even more different. Interesting. I thought this was the exact same board that we have here, but it seems like it's not. It's just close. Okay, so this might be a different revision then. So I will be looking into if I can flash the BIOS properly or not. Let me do that. So now I've gotten the exact same one. And let's see again. This resistor is still the same. So we got lucky on that. But now if we look at this area, now the SPI chip's actually here, which is a 128 one. Yeah, this is what I expected. And it is still a 1.8 volt chip. And let's see, this component isn't soldered in, which it is, and it was this component. So all of the components are still there. But what you can see, pin 1 is connected to there, pin 2 connected is to there, pin 3, pin 4, pin 5, pin 6, pin 7, and pin 8. So we can just use directly this header here to program this chip. So there's actually a really important lesson to teach here, because this is a ASUS BIOS, and they probably had probably everyone who has tried to program an ASUS BIOS had this problem before. You can only get .cap files from the actual ASUS side, which is not the exact size that you need for flashing it into the BIOS EEPROM. So I will show you what the actual size is. I will be getting the original dump, or the dump that is on this chip right now, onto here, and I will show you. So now you can see the difference. We have the dump off of the chip, and we have the BIOS.cap file that you get from ASUS, which has 16.386 kilobytes, and the actual one has 2 kilobytes less. And this is because of the header file that is attached to the .cap file. And we will be extracting the right BIOS out of this now. Let me show you how you do that. You need a tool that is called UEFI tool. And with this tool, you're going to open up the image. Let me do that. You have the .cap file now loaded, and you go into the AMI APTO capsule, and you actually have the UEFI image right here. This is the BIOS that you need. You're going to right click that and going to press extract as is. And now you can see we have an image UEFI image, an extracted image from this cap file, which has 2 kilobytes less. And this we can now put onto the chip and program onto there. And this is the actual BIOS that we want. So I'm now pretty confident that it will work. Maybe I will eat my words, but the BIOS was definitely wrong on that. I seen the cap file that was on there, and they didn't cut off the header of the BIOS, and there was actually a big portion of it that was just garbage written into the BIOS. So yeah, this is a mistake every beginner does, because ASUS just did it that way, and it's so confusing for everyone. And yeah, people just proceed with the BIOS flashing, even though they get a warning that the file size is not the correct one. And yeah, you will just not have a right BIOS and not working board. So that also explains why we didn't have any postcodes and nothing. So let's see now for the passive power consumption what we will have. And power consumption still looks the same, but let's see as soon as we press the power button now. And there we are. We now have postcodes running on here. We don't have postcodes on here, so we do get rid of that. And the amperage is changing, as you can see. So I will have to get a post screen on here. Probably am too late. There was a BIOS. There's a beep already. And there's our post screen. Very, very nice. There we go into the ASUS BIOS, and everything's working. That is very nice to see. And you can see the power supply is still running very fine. As you can see, we are in the board with the current limit of 5 amps. That just worked without any problem. So there's only one thing left to fix on this board, which is this PCIe latch. Let's quickly also do that so that this board will be completely fully functional. I will be doing the stress tests offline, so like not on the video, but I'm pretty sure they're just going to pass, because we had the dead BIOS and also the resistor that was wrong here. And yeah, let me connect also another stick of RAM in here. But first we're going to be fixing this PCIe latch. So in my last video I showed in detail how to get these small things out of here. And yeah, we will be just plugging it in here now. Let's see that this will go into its respected place right there. And now we have the PCIe latch in here, and now fully working. Beautiful. And now the latch is also there and also working. And yeah, let's just once more, with this time more RAM, let's just turn it on again and see our power supply in action that was sponsored to us by FNIRSI. And I'm just very thankful. I will be having links to those products in the description also. And yeah, I'm very thankful. They have way more stuff for testing electronics. They focus on producing electronic test equipment, and I will be definitely be having a look at what I also have in stock. And let's see if going into Windows will actually pass the current limit this time or not. I'm very interested right now. We don't have a GPU in here, which save us quite some amps, so let's see for that where this is going. Let me still thank them, and yeah, this will be a great addition for our YouTube channel with us now having this awesome view of the amperage going into the board, which is way easier readable. And yeah, I'm very thankful. I hope you enjoyed this repair. Previous technician really had a good thought of mind. Like, big respect that they found the actual problem with the resistor, but finding the actual value for that is really difficult if you don't have a board view. And also the need of needing to know how a BIOS flash works on ASUS boards. Like, ASUS is the big trap when you need to flash a BIOS. Like, that's just sadly how it works, and you have to learn that. And yeah, what can I say? If you ever have to flash a BIOS on an ASUS board, you now know how to do it, how to extract the actual BIOS image out of the .cap file, and you won't do this mistake. But I hope you enjoyed this video. I hope you enjoyed the repair and you actually learned something in all of this endeavor. And yeah, this was Mainboard Medic. All of my tools are linked in the video description. Thank you very much for tuning in and being here with me. And yeah, thank you very much and goodbye.